Hari Om. In this session, we discuss how an atom acts as a magnetic dipole. As per the heading, you can see magnetic dipole moment of a revolving electron. The revolving electron can produce magnetic moment. How it is, let us see. Now, if I consider an unpaired electron in the valence band of an atom of nucleus having Z times E, a heavy nucleus, around that the electron is moving in the anti-clockwise direction, and therefore that constitute a current I in the clockwise direction. Now this current moving along the clockwise direction produces a magnetic dipole moment which is pointing into the plane of the loop. Now this electron, when it goes around the nucleus in a circular orbit as per Bohr model of atom, this electron movement will be moving with a definite frequency and definite time period, and therefore we can consider the movement of the electron to be constituting a current loop around the nucleus. Now, the current constituted by this electron can be taken as current I, which is equal to E by T. E is the charge and T is the time period. Now, this you can convert it into E divided by time period. You can take it as 2 pi by omega, where omega is the angular velocity of the electron moving around. That will be equal to omega equal to 2 pi by T, and as it is moving around with a definite angular velocity, it must be having a linear velocity along this direction, let it be v. That v will be equal to r omega. These are all the basic things relating to this, and therefore now you can find that this will be equal to current I is equal to E omega divided by 2 pi. Now what is the magnetic dipole moment of those revolving electron? The M will be equal to current into area of the loop. We just now discussed current into area of the loop. That will be M equal to current I, you can take it as E omega divided by 2 pi into area, I can take it as pi r square. Now what of this? I can have magnetic moment M, therefore will be equal to pi and pi cancels, and you will be getting E omega r square by 2. This is one equation for magnetic moment associated with the atom. Now applying this formula over here, I can take this M to be equal to E into V into R by 2. Another equation. Okay? The equations that I put in the box, all these are very, very important for the entries. Now here we are getting that M equal to EVR by 2. E is the electronic charge, V is the velocity of movement of the electron, and R is the radius of the orbit, and all that. Now, you see that according to Bohr model of atom, this revolving electron can occupy n number of different energy levels. That means depending upon the energy of the revolving electron, its position can be changed. It can occupy n number of different energy levels. So how to bring that level into this? Let us see. For that, we will be making some adjustment here. So let me erase off these equations and let us multiply this with m. You get capital M, that is equal to E into m into v into r divided by 2m, where m, small m, is the mass of the electron revolving. Then m and m cancel, you get the same thing only. But now you can see this m into v into r is nothing but a new quantity we introduced here. You already studied that it is L divided by 2m, where L is called angular momentum of the revolving electron. L is equal to angular momentum of the revolving electron. You studied this angular momentum and all last year. So, angular momentum is also a vector quantity, and therefore you can find from this that as the electron is revolving in the anti-clockwise direction, its angular momentum depends on this omega. Omega is also along this way, velocity also along this way. Therefore, the angular momentum will be directed towards you as per the rule. So, for the electron revolving in this case, the angular momentum vector and m vector will be in the opposite direction, and therefore you can put a negative sign over here. But if it is a positive charge revolving, you can find that the direction of flow of current and the direction of motion of the charge, positive charge, will be the same, and therefore for the positive charge this moment will be equal to E into L divided by 2m, because the angular momentum and the magnetic moment will be along the same direction. Okay, now you got a formula introduced here, that angular momentum. This angular momentum we can treat to include that levels into the equation. Let us see how it is. Take down this and let me erase off this one, and let us see this one, that from here I get m by L. I introduce a quantity m by L which is equal to E by 2m. I am taking only the modulus here, the magnitude only. Okay. So E by 2m, when I take E by 2m, I am getting a quantity m by n. This quantity is called gyromagnetic ratio for the revolving electron. Gyromagnetic ratio for the revolving electron. And if you substitute the values of this electron charge and mass of the electron here, you can find that for the electron this will be coming around 8.8 into 10 to the power 10 coulomb per kilogram. So this is entirely new quantity. Just keep in mind gyromagnetic ratio, and its value is 8.8 into 10 to the power 10 coulomb per kilogram. Now let us consider that levels into this, that according to Bohr's quantization condition, you studied Bohr's force laws. According to Bohr's force laws, based on Bohr's force laws, we can have the angular momentum of the revolving electron as quantized, and that angular momentum of the revolving electron L will be equal to an integral multiple of h by 2 pi, where this h is called Planck's constant. You all know what Planck's constant is. So h is called Planck's constant. So h by 2 pi into n. This n can have values ranging from 1, 2, 3, etc. up to infinite. All whole numbers you can consider. No zero level. And if I take this into this particular equation and rewrite it, I can have m will be equal to E into L divided by 2m, and therefore m equal to E by 2m into n h by 2 pi. And together I can have m will be equal to n times E h by 4 pi m. E h by 4 pi m, n times u. So the magnetic dipole moment associated with the revolving electron can be equal to n times n h by 2 pi, and n times E h by 4 pi m. Now you can see this E h by 4 pi m. This quantity is a constant, and you can have the value of that one, and that constant value into n. That means the magnetic dipole moment associated with the revolving electron is also quantized. So it will depend on the level in which the electron is revolving. And the value of that constant, if I take that constant value E h by 4 pi m, E h by 4 pi m is denoted by mu b, or we call this as Bohr magneton. Bohr magneton for the electron, and it is coming around 9.2 into 10 to the power 24 ampere meter square. Exactly, let me write that value exactly. The value is coming around 9.27 into 10 to the power minus 24 ampere meter square. Ampere meter square is the value of Bohr magneton. Okay, so here the revolving electron will be having a constant value of magnetic dipole moment, and that is multiple of integral multiple of Bohr magneton you get. Okay, so in effect what we are saying is that an atom with an unpaired electron and a valence band will be possessing what you call a magnetic dipole moment, and we call that magnetic dipole moment as atomic magnetic dipole moment. Atom acting as a magnetic dipole. And this type of atoms defines the magnetic behavior of the material in effect. So this part is very, very important in the discussion of different types of magnetic materials. So here we understood terms like gyromagnetic ratio, remember that, Bohr magneton and its value. This is all for electron. If you write it for proton, this mass will be changing and therefore the value will be the same. Alright. So understand all these things. Atom with an unpaired electron, the valence band, will be possessing the magnetic dipole moment, and that magnetic dipole moment is called atomic magnetic dipole.